Alrighty, so we finished talking about quadratics in chapter 2.1. In chapter 2.2, we begin to talk about polynomials of higher degrees. All right, so as you guys know, a quadratic is a polynomial of degree 2. All right, we're going to be talking now about polynomials with a degree greater than 2. So by definition, here we have a polynomial. Let n be a non-negative integer and let a subscript n, a sub n minus 1, comma, dot, 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 a sub 2, a sub 1, a sub 0 be real numbers with a sub n does not equal 0. The function given by f of x is equal to a sub n x to the nth power plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a sub 2 x squared plus a sub 1 x plus a 0 is called a polynomial function of x with degree n. Now, I know that's all very, very, very confusing. The important part to take away from this, okay, is that when we are talking about the degree of the polynomial, we are referring to the highest power of x. All right, the highest power of x. That will be the degree of the polynomial. All right, polynomial functions are continuous for all values of x. There are no breaks, holes, or gaps. Also, polynomials have smooth, rounded curves. In other words, there are no cusps or sharp corners. All right, just a quick thought on what it means for a function to be continuous. All right, this is a really kind of rough definition, but basically a function is continuous if you can draw it without lifting up your pencil. All right, so notice in this case, if I wanted to actually sketch this graph, well, I'd draw this first piece of this piecewise function down with this line, and then in order to get to the next piece, I'd have to lift up my pencil and come back up to the top here. All right, because I had to lift up my pencil, that means that I have a discontinuity. So this is most definitely not going to be an example of a polynomial. All right, also here, this function has a cusp or a sharp corner at x equals -2. All right, so this is not going to be a polynomial function either. All right, polynomial functions have smooth, rounded curves. Another example of a cusp in a function that we have dealt with is going to be your absolute value function, which forms that V shape. All right, that also has a cusp in the graph, not a polynomial function. All right, so polynomials are continuous for all values of x, and they have smooth, rounded curves. Now, the most basic form of a polynomial function is a monomial function. All right, the prefix mono means one, so monomial functions are polynomials that only have one term. All right, yes, I know it's interesting. Monomials fall under the category of polynomials. All right, monomial functions in the form f of x equals x raised to the nth power are referred to as power functions. If the degree of n is even, the graph of the monomial function y equals x to the n will touch the x-axis at 0, 0, and will go through the points 1, 1, and -1, 1. All right, now it's not critical that you get this information into your notes, right? But what you should look at in these next few parts here is just the relationship between different types of monomial functions. So for example, here I have my graph of y equals x squared. Okay, this is a power function of degree 2, right? The power is 2. Notice it's a monomial function because there is only one term in the function. And it has this nice parabolic shape, and it goes through the origin at 0, 0, and also goes through the point 1, 1, and -1, 1. Notice the y-axis is scaled by 2's. Okay, well, let's now compare the graph of y equals x to the 4th. Right, this is a power function, monomial function of degree 4. Notice it has the exact same x and y intercept. It goes through the origin. It also crosses through the point 1, 1 and the point -1, 1. However, the graph is much more steep outside of -1 and outside of +1, and the graph is actually flatter in between values of x between -1 and 1, right? And that pattern continues as we increase the power. Here we have the graph of y equals x to the 6th. Notice outside of 1 and outside of -1, the graph grows more quickly. And between x values of -1 and 1, the graph is actually flatter. Okay? Here is y equals x to the 8th power. Again, grows even more quickly outside of -1 and outside of +1, and is even flatter between -1 and 1. But what points do all of these graphs have in common? They all go through the origin here at 0, 0, and at 1, 1, and at -1, 1. All right, so just keep those shapes in mind. It'll give you a good idea of what we're looking at in some of our future graphs that are coming up later on. All right, well, what if the power is odd? Okay, if the degree of n of our monomial function is odd, y equals x to the nth will go through the x-axis at 0, 0, and go through the points 1, 1, and -1, -1. All right, notice here we have a monomial function. This is a power function of degree 1. Yes, it is implied that this is x to the first power. And you guys all know what y equals x looks like. That's just a line with a slope of 1. And yes, it goes through the origin, goes through the point 1, 1, and goes through the point -1, -1 here. Our next monomial power function of odd degree would be x cubed. And here is the graph of x cubed. Now notice, it goes through the origin as well, passes through the point 1, 1, and the point -1, -1. But outside of -1 and 1, the graph grows more quickly. In between -1 and 1, the graph is flatter. Okay, noticing a pattern, hopefully. Y equals x to the 5th. Here is our next odd power monomial function. Well, outside of -1 and outside of 1, the function is going to grow and fall more quickly. Between values of x, in between -1 and +1, our graph flattens out. What do you think the graph of y equals x to the 7th would look like? Very similar shape. Again, it's going to grow more quickly outside of 1, fall more quickly outside of -1, still goes through the origin at 0, 0, and still crosses through the ordered pair 1, 1, and -1, 1.